Hadi, it's available now?
Yes.
طيب. Okay, بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome to EE21. So today's lecture will be the 19th lecture. And in this lecture, we're going to continue talking about, starting from chapter 7, we're attempting to study the temporary or the transient behavior of RC and RL circuits. So if you recall in the first, Yasser, yes?
Yes, Doctor, can you share the screen again?
It's shared, okay. So let's see. It's there actually. But let me.
Maybe you can share it again. Yes, now I can see it. Thank you.
Starting from chapter 7, we're trying to study the transient behavior of RL and RC circuits. So if you recall, we started with what happens when when the capacitor and the inductor are initially charged. Then all of a sudden, these elements are being discharged. So that's the first part that we studied. This response or this behavior or this this response is called natural response. Then last time we started talking about step response, and that specific response, what we have, the situation is slightly different. So the capacitor and the inductor, they were not charged initially, or they could be charged as well. Then all of a sudden we apply a source. So we were attempting to study the. We started with the circuit that has inductor and resistor, RL circuit. And if you remember, we derived the current and we derived the expression for the current, and we stated that the current in such a circuit is given by this formula: I of t equals to I final, the final value of the current, taking the limit as t approaches infinity, plus I naught, which is the initial value, the time of switching, minus I final, which is again the final value, scaled by this natural exponent, and of particular importance to us is tau, which is the time constant, L divided by R. Again, the unit for tau is actually second because it's a time. And in this case, it represents the value or the time needed for the inductor to reach for 63% of its final currents. Okay. What's left in this part is actually solving an exercise, and this is an exercise that we did not have time to do last time. So let's attempt to solve it. It's not a very complicated exercise. Again, don't get frustrated by the very long statement. So let's see what we have. So we have the following circuit. This is the circuit that we have. The circuit has a switch. The switch was initially at position A, then it moves to position B at t equals to 0. And we are asked to find I of t for t greater than 0. What's written here is actually very important, but it states that the switch is a make before break type. So it's very important that you switch while you're maintaining the continuity, so there is no abrupt change in the current. And that's exactly what happens. Okay. So the first thing is we are asked to find I of t for t greater than 0. So let's see what we can do with this. For any circuit like this, it's very important to do it's very important to draw the circuit to divide the analysis of the circuit into two intervals. So we have the time before the switch moves to position B and the time after the switch moves to position B. So let's subdivide, or let's divide this problem into two sub-problems. So the first one, from the first case, from the case when the switch moved to position B, from the case when the switch at position A, what we can infer here, what we can find is actually the initial current. Because remember here, in order to solve this, in order to find the expression, I need the initial current, I need the final current, and I need the time constant. This is the expression. I don't need to derive it. It's there. Okay, we did derive it. All what you need is the initial current, the final current, and the time constant. So from the case when the switch at position A, because this is a situation for t less than 0, we can get the initial current passing through the inductor. Okay. So what's the initial current? The initial current here, Ziad?
Is 8 ampere because it doesn't change instantaneously in the inductor.
What's the value?
8 ampere.
It's partially correct. It's not exactly 8. It's actually negative. The reason for that, at DC, you will see that the circuit will behave like this. And this is the direction of the current that we are interested in. So 8 ampere is flowing the other way around. That's why we have a negative. So the initial current is negative. Ali, question or trying to answer?
No, that's me.
Okay. Right. Okay. When the switch moves to B, let's see what we have. Again, the very first step is actually to draw the circuit, because this is going to give me an indication on, or like this is just going to give me a very useful visualizing aid here. So 24 volt, I have 2 ohm, and then I have the inductor, 200 milliamps. And I'm interested again in the current here. Okay. So from that, what can we say about the final current? Abdullah al-Shriri.
It equals 12 minus 20E.
Equals to 12. What?
The current, it equals to 12 minus.
No, okay. No, I'm interested in the final current. So what's the final value of the current here?
I'm not sure.
Okay. طيب مهند.
I think it will be 12 ampere since
Yeah.
it's 24, no?
Yes. Since
It's
what?
they're all in series, so the current passing through all of them will be the same. And by using Ohm's law, I will have 24 divided by the resistor to get the current.
So what happens to the inductor here? Why did you ignore it?
I don't know.
Okay, so all of a sudden you decided to ignore it. يزعل عليك.
I thought I have to find the current before the inductor, so I just ignore it.
Okay, no, you cannot just simply ignore it. There's a reason for ignoring it. Yeah, Ali Talib.
Because it's in the final position.
Yes, because the switch been closed, the switch been at position B for a very long time. So we're taking the response, the DC response of the inductor, and the DC response of the inductor is actually the inductor will behave like a short circuit at DC. So that's why you ignore it. You can't just simply ignore it without any reason. So now I have the initial current, the final current. I need to find the time constant. Okay, so what's the time constant here? The time constant is L divided by R. Okay, 0.2 divided by 2, which is 0.1 seconds. So the expression for the current is now straightforward. So I final plus, in this case, I initial is minus 8 minus I final, which is minus 12. So the total will be 20. T to the power T divided by tau, which is 10. The unit is ampere, and this is true for T greater than or equals to 0. Okay. We found part 1. Part 2, what's the initial voltage across the inductor just after the switch being moved to position B? Okay. So let's go back to the statement and think about what we've been asked about. So we're asked about to find the initial voltage after the switch, just after the switch being moved to position B. So at T equals to 0 plus. Because remember, at T equals to 0, the voltage is not defined. At T equals to 0 minus, in this case, the voltage is 0. So what happens, how to find the voltage at T equals to 0 plus? How to find the voltage at T equals to 0 plus? I need someone other than Ziad. Okay, I have 35 students here. Okay, Rahim.
I think it's 0. So
No, it's not 0. Yes, sir.
maybe you can use the equation V equal L di dt.
Yes. So let's use
And then we have
exactly. So V L di by dt. We do that, we'll get 40. And this is true. Now we need to substitute. And this is going to give us 40 volts. Sorry. Okay, so it used to be 0, then jumps very quickly to 40 volts. Okay, how many milliseconds after the switch has been moved to does the inductor voltage equal to 24 volts? So what we need to do is the switch, or the inductor voltage here, if you can see the equation here, it starts with 40, then it will start decreasing until it reaches 0 at T equal as T approaches infinity. So what we want to do here, what we want to find is actually we want to find the time needed for the inductor's voltage to reach 24 volts. Any comment? Any suggestion? طيب, Ali, Ibrahim, you all participated. Thank you very much. I need a new fresh blood here. Hadi.
Put the equation equal to 24.
Exactly.
And we'll get that up.
Okay, so let's do that. So if we solve for it, we'll get 1 over 10 natural logarithm of 40 divided by 24, and the solution here is 51 milliseconds. So after 51 milliseconds, the inductor voltage will reach 24 volts. Ali, question? Okay.
No.
طيب, okay, let's see what happens here. The fourth part is asking us, does the initial voltage make sense in terms of the circuit behavior? So let's see why in particular he was interested in this question or in this part. Let's see the circuit here. So after the switch moved to position B, you have a 24 voltage source in series with an inductor and series with 2 ohm resistor. And if you measure the voltage just immediately after the switch moved to position B, you will see that the voltage is 40 volts, right? And that's what we found in part 2. But how come you have a battery of a 24 volt and you have a voltage across a specific element that's actually greater than the battery's voltage? This doesn't make sense. You see what I'm saying? Had a question or participation?
Participation.
Right, okay, hold on a second. Okay, Abdulkareem, what do you think?
Well, it's an inductor and there was a current source. So, and inductors store electric energy.
Okay, it's partially correct what you're saying. Partially. So, yes, there is an inductor. The inductor is storing magnetic energy, not electrical energy. So they're kind of like a source of energy in the circuit caused by the fact that we have an inductor here. Since we have an inductor, so we will have a source of energy in the circuit here. So the answer, is yes. So the inductor so we can check that by applying KVL. If you apply KVL here, you'll get minus Vs, which is minus 24, plus 2, the current, just immediately after the switch been moved to position B, plus the initial voltage equals to 0. And in this case, you will get minus 24, or let's say we're interested in finding V naught here. V naught will be 24 minus 2, I naught which was minus 8, and this is going to give me 40 volts. So yes, it makes sense because the fact that we have an inductor made it possible to have an higher level of voltage in the circuit. So the last part is asking us to plot I and T versus time, and we can do that. I don't want to spend time on this part. But you can see here that is it asking us for T? Okay. We're talking about I, in this case, then it will be something like this. Again, the scales are not the same, so this is for I. For T, For V, it's something like this. All of a sudden, then so the scale is not the same. So here is 40, and here is -8, and this value is 12. Right. Okay, so that's what we did when we have RL circuits. That's what we did with the step response. Let's see what happens if we have an RC circuit. I mean, the first case that we did was with an inductor and a resistor. In this case, we're concerned about the case where we have a capacitor and a resistor. Okay, let's see what happens. Right. Okay, let's derive the form of the step response of an RC circuit. So the derivation is actually similar to the case where we have an inductor and a resistor. The only difference here is that we need to. The only difference here is that the key quantity is actually the voltage across the capacitor. And the other thing here is we need to apply KCL instead of applying KVL. So how many of you tried to rework the derivation that we did last time? Or how many of you is used to rework the derivation that we usually have in class? Please raise your hand. Nobody? So nobody ever tried to rework the derivation that we had in the class? Any derivation that we had? You all take the final value?
I mean, we read it and trying to understand, but not work it or rework it.
Okay, this is not a good thing, Shabab. The reason for actually showing you the derivations is so, first of all, it's very important that if you can derive it, try to derive it. It's very important. There are multiple reasons for that. If you derive something, then you understand almost everything about the problem, because you cannot move between one step and from one step to another without understanding what you're doing. Otherwise, you are memorizing the derivation. So if you want a better understanding of the concepts in this course and in any other course, please try to rederive everything. It's really important. Okay, if we apply KCL here, what we have IS is entering the node. Then V divided by R, which is the current, VC divided by R, which is the current passing through the resistor. And we have the current of the capacitor, which is from the expression dVC by dt. So if we rearrange the solution, we'll end up with something like this. If we rearrange the equation, we'll end up with something like this. 1 over RC DC plus IS divided by C. Okay, if you recall, this is exactly the same differential equation that we had with the slightly different coefficients. So we expect the solution to be of the same format. طيب, I can simplify it to something like this. طيب, this is the voltage. If you want to find the current, I need to differentiate it. Probably differentiate the first equation. So for the current, I'll come back to your question in a minute. Okay, we see it's exactly the same part. So we need to find the final voltage. We need to find the initial voltage. We need to find the time constant. And remember, tau, since this is an RC circuit, so tau is actually tau is actually R multiplied by C. Ahmed?
دكتور الحين الاي اس اللي فوق ماينس صح؟ وانت وديتها الجهه الثانيه صارت بوزيتيف.
Yes.
وبالنسبه للسي سي دي في اوفر دي تي.
We assume all the currents are leaving that node.
اوكي ثانكس.
طيب. Okay, let's try to solve an exercise here. So in this circuit, we have a switch. The switch used to be at position 1 for a very long time. Then at t equals to 0, the switch moves to position 2. We need to find V naught for t greater than 0. Right. Okay, so let's try to find V naught for t greater than 0. Ibrahim?
Actually, Doctor, I was gonna ask you about the derivation.
Yes, go ahead.
Vs here in the first line.
Yes.
Where did it go in the second when you rearrange the equation?
Hold on a second. I see. The second line is kind of like is taking VC, multiply it, or this one is actually VC. Because it's in parallel with the capacitor, so it should be exactly the same. So that's exactly the value here. The actual derivation is actually in the book. We did not deep dive into the derivation because it's similar to the derivation that we had when we did the RL circuits.
Okay, thank you.
Okay, so going back to this problem, Let's see what we have. We have a circuit with the switch. The switch used to be at position 1 for a very long time. Then at t equals to 0, the switch moves to position 2. And what we want to do here is we want to actually find the expression for V naught of t, which is the voltage across the capacitor for t greater than 0. So let's see what we have. Or what's the best way to approach this problem? What is it?
Yes, first we can find the initial V0
Okay, exactly.
when when the circuit at position A, or
Yes.
the capacitor will act as open circuit.
Exactly. So let's, okay, this is excellent. So let's draw it.
Yes.
We have a 40 volts. We have 20K. We have 60K. And we have a capacitor, but it's been at position 1 for a very long time, so the capacitor will behave like an open circuit. Type, what's the value, Walid?
We can use VDL to find the V0, which is 40 multiplied by 60K over 80K.
I will give you the solution here. It's 30.
Yeah.
Okay, very good. So now we found the initial value. The next step is we need to find the final value. So the final value can be found using the case or using the situation when the switch is moved to position 2 and stay there for a long time. So let's draw the circuit on the switch. Position 2 for a long time. So I'm just drawing this part of the circuit. 8K, 160, 40K. This one is 75. So what's the final value here?
Minus 60.
Exactly. So 160, 40 plus 160 multiplied by 75, and this is going to be minus 60 volts. So now I found the final value, the initial value. What's missing here? شباب. طيب let's see. The Kareem.
I need tau.
We need tau. So tau is
So,
F9 multiplied by C. Okay, so what is R7 here? So if I take this part, make a bit here. Shabab, this is part of your midterm. So what is R7 here? Seen by the capacitor. Okay. Abdullah al-Jariri.
The 40K ohm and 160 are in parallel.
Yes.
Then we add to the 8K.
Exactly. Because we deactivated the voltage source. Okay, now we have everything. We have R Thevenin, we can easily find tau. So if we substitute here, tau will be 10 milliseconds. So now we can easily find the expression of V naught, V final, which is minus 60, plus V initial, which is 30 minus 60, equals to volt, and this is true for t greater than 0. I can simplify it to something like this, minus 60 plus 90, e to the power minus 100t volt, and this is true for t greater than or equals to 0. Abdul Karim, question?
No, I understand.
Ahmed, question?
لا كنت بشارك شكرا.
Ziad, question?
Yes. Is there certain types of switch for the circuits? Is it for RL or RC or both?
At this stage, we don't care about what type of switch we have. So it could be any type of switch, mechanical switch, electronic switch, etc. So it could be any switch.
Okay.
Or we could be like, we present the switch as, we model like the behavior as having a switch, but just could be like you take the battery and you connect it to the circuit. Or you disconnect the circuit simply. So we did not actually spend time on doing this, on defining what type of switch that we have. Okay, so the second part is asking us to find I naught, which is the current passing through the capacitor. So now if you know the voltage across the capacitor, can you find the current passing through the capacitor? Okay. So I need to take only the derivative, scale it by C, and this can give me minus 2.25 e to the power 100t, negative 100t milliampere, and this is true for t greater than 0 plus. Okay. So let's pause here and think about what we did. So what we did so far, we studied the case where we have a resistor and capacitor, and we applied the source here, and this is what we call the step response. We did the same for the case of the capacitor and for the inductor and resistor. It turns out there's some standard way of solving this problem. What we did was kind of like unsystematic way, but in general there is a systematic way of solving any problem that involves having a resistor, a capacitor, and an inductor initially. So if you go back to the derivation that we did, you will see that in all cases we have the following differential equation. We have the quantity that we are interested in, could be the voltage or the current, could be the voltage across the capacitor or the current passing through the inductor. We have tau, which is the time constant, and we have k. K is K here is a term. If it's 0, then we have the natural response. If it's non-zero, then we have the step response. It turns out the standard way of solving this problem is, we will not deep dive into the details because this is part of the differential equation course that you're going to take. You will see that the solution of such a problem has the following form. It has the final value the initial value minus the final value plus an exponent term. Here, remember, in the previous analysis, we assumed that T naught is 0. The initial time, the time when we switch or when we move the switch from one position to another, is 0. But it could be actually any time. The only thing that you need to do is actually you need to, first of all, the initial value is evaluated at that specific time, and you need to shift the exponent term by the initial time here. And of course, this will be valid for usually. So this could be plus or could be just as it is. If it's plus, it means that we're talking about the voltage across an inductor or the current passing through the capacitor. If it's a standard way, then we're talking about the quantity that does not change instantaneously. Okay, let's attempt to solve an exercise on this. Yes, Ibrahim.
Doctor, for T0, is it like the time needed for the switch to change the position, or?
No, it's actually the time when you make switch, when you switch the when you switch from one state or from one position to another. We usually assumed it's 0. If you have one switch, you usually assume it's 0 because you kind of like have an absolute. You kind of like make your own time reference, but the situation is not going to be the same if we have. Let me jump very quickly to this problem, for example. This is in the following section. In the following section, you have sequential switching. So it's at position A that moves to position B that moves to position C. So at T, for example, T equals to 0, it moves from position A to position B. Then you cannot just assume, you cannot just ignore what happens. I mean, you need to set the tape because you want to study quantity, or you have multiple switching times. So you need to set one time reference here. So you'll see that the response of when the switch move, we're talking about VT here. When the switch at position from position A to position B, it's evaluated at T equals to 0. Then at T equals to 15 milliseconds later, the switch moves to position C. So in this case, the response of G of T when the switch at position C is evaluated at T equals to 15 milliseconds. So that's the only time you need such a thing.
Okay, I got it. Thank you.
Okay, so you see here the switch is at T equals to 0. So the switch in this circuit, the following circuit, used to be at position A for a long time. Then it moves to position B at T equals to 0. So what we're asked to do is, at this stage, because I introduced the standard way of solving this problem before actually we cover it in that specific section, you will see that everything here is familiar with. Everything here we are all familiar with. So we're asked to find the voltage across the capacitor here at T equals to 0, or what we are asked to find the initial value of the voltage across the capacitor. So what's the initial value of the voltage across the capacitor? Mohammed?
The initial value of the voltage will be equal to the voltage across the 60 ohm resistor, and we can find it by using VDL.
Yes, exactly. So let me just draw the circuit here. So VI will be 60 plus 20 multiplied by 40. And this one is going to be 30 volts. Okay, so what's the final value of VC, Rahim? So let me draw the circuit here. Rahim? Rahim, you're muted. Okay, you are muted. Yasser?
Yes, the final value is going to be, after a very long time, the voltage across the capacitor is going to be 90.
Okay, 90 volts.
Yes.
Okay, exactly. So we found the initial value, we found the final value. So what's the time constant when the switch is at position B? So the time constant here is again what? Walid,
Yes, 0.5 multiplied by 0.5 micro multiplied by 400K.
Okay, exactly. Tau equals to RC. R here is 400K. C is 0.5 micron. So the time constant is 0.2 seconds. Okay. Now we are asked to find the expression. So we have everything we need. We have the final value, the initial value, the time constant. So the expression will be okay, of VC is going to be 90 minus 120 the following part is asking us to find the expression for I of t for t greater than or equals to 0 plus. In this case, Ibrahim.
We should derive the voltage multiplying by 6.
Exactly. So what we need to do is actually take the voltage, differentiate it, and scale it by C. And this can give me 300 e to the power minus 5t microampere. And this is true for t greater than 0 plus. Okay. Bye. The following part is asking us to how long after the switch is in position B does the capacitor voltage equals to 0? Okay, so what we want to do, we want to find, because remember here, the final value of the capacitor is 90. The initial value is minus 30. So there is a point in time where because it will start at minus 30, then it will increase until it reaches 90. So there's a point in time when the voltage across the capacitor is 0. What's that point? What do you think, Shabab? Okay, Mohammed?
We can take the equation of VCT and replace VCT with the 0 to find the time.
Exactly. So if we do that, we'll end up with Okay, so if I take the natural logarithm of that, I will end up with t equals to natural logarithm of 4 divided by 3 divided by 5, and this is going to give me 57.54 milliseconds. Okay, so at t equals to 57.54 milliseconds, the value of the voltage across the capacitor reaches 0. So we're asked to plot VC of t and IT versus t, and this is, I'm not going to spend time on it, so I'm just going to throw it like this. Again, drawing is not to scale. If you want to find the inductor or the current, it's something like this. So this is 300 mic. This is I. This is V. I just want to point something out that the axis, the time axis is the same, but the y-axis is actually not the same. So everyone has, or every quantity has its own scale. Okay, so I want to make the following comment here. خلينا نشرح. Okay, can you observe anything here in the circuit? There's something observable here. So, yes, Ziad.
Voltage source is not drawn as usual.
This is one thing, yes. This is maybe another symbol for sources. But it's very important here that you have Mohammed.
Maybe that we have 2 voltage sources.
Not really, the Kareem.
One of the resistance is way bigger than the other 2.
Yes, that's one thing. That's the thing that I'm looking for. So one of them is, or two of them is 20 and 60. The other one is 400 kilo ohm. So why do you think, or one of the greatest application of RC circuits is actually in converting an AC source to a DC source? But again, this is not part of this course, but it's very nice application. And since we have a luxury of time here, we have the luxury of time, so we are ahead of the syllabus. So we can do we can spend a few minutes on that. So just let me and big. All of you, I'm assuming, electrical engineers or CISE students or COE, so you will eventually take EE203. If in EE203 you will have something like this, you have a source, you have a device that we're going to explain in a minute, and you have a resistor here. So if you take the source here and try to plot the voltage versus time, you will see that it's something like this. So it's not constant, it's fluctuating. If you try to take this one, V naught, you will see that and plot it. You will see it's something like this. What happens is the following. You have an AC source, VS, and that AC source is being replaced by something quite weird. This is not exactly what we want. What we want here is we want to have an AC source, because this is the source that comes from the power outlet, and change it to a DC source. A DC source is if you have, for example, your laptop, your laptop needs a DC source. It doesn't need an AC source. So you want to convert it to something you want. Something like this. Something constant. So what should you do? First of all, what is this device? This is called diode. It's a nonlinear device, so the relation between the voltage and the current is not linear. And one important property of this one is that if V output then it will behave like a short circuit. Okay. So one is short, one is open. So let's see what happens here. If you have a resistor, then the resistor cannot store energy, cannot store voltage. So as long as the voltage is positive, this diode will be on. So means it will be a short circuit. So whatever voltage at the source will appear at V0, and this is what we have. So in the positive cycle, we have in the positive cycle we have the voltage here. In the negative cycle, the diode will behave like an open circuit, so there will be no voltage. So if you measure the voltage across the resistor, it will be 0 because there's no current passing through the resistor, and it will keep repeating itself. So what happens if you add a capacitor here? You take this one, you said, well, I'm going to take this device and okay, let me add another page. You said I'm going to add a capacitor. So V0 now is the voltage across the parallel combination of the capacitor and the resistor. It's not only across the resistor. So what happens here, if you plot the voltage across the capacitor or the voltage, the V0, it will be something like this. Take it, try to plot it. You will see it will be something like this. So it will start 0. Then when the capacitor, when the diode is off, in this case, it behaves like an open circuit. It's like a switch. So the capacitor will start discharging. Then because we have a source that keeps, we have a periodic source, so the source will be positive again. So it will start charging here. And to start discharging when it's in the negative cycle, then charging, then discharging, and stay for there. It seems that if you play with the value of the capacitor and the resistor here, basically what you're doing is you're playing with the time constant. You're playing with tau. So if you play with tau, you can actually make the response as something like this. Which is almost like a DC. You need some other circuit element that's going to smooth things. So this is one of the very neat application of capacitors, and you will see it inshallah when you take AE2. Any question before we move? So just keep the analysis that we have in mind, and when you take AE203, just say, okay, we did this in AE21, we talked about the time constant, and we saw that if we increase the time constant, the discharging time will be longer than the discharging time if we have a short time constant. Okay, let's go back to AE21. Let's see what we have here. We have a switch, and the switch has been open for a long time. At t equals to 0, the switch is closed. We want to find the expression for I of t for t greater than 0 and v of t for t greater than 0. So what do we need here? شباب we need to find I of t, the current passing through the inductor, with the switch for t greater than or equals to 0. So let's actually draw the circuit as, or let's analyze the circuit. So the initial voltage of the capacitor is actually 0 here, because the capacitor is not being charged. So if the initial voltage across the capacitor is 0 just before the switch is closed, the value of the capacitor's voltage should be 0 just after the switch is closed, because the voltage across the capacitor cannot change instantaneously. What circuit element we have that has a 0 volt? That always have a 0 volt? Go ahead.
Short circuit.
Exactly. A short circuit is a circuit element that has a 0 volt. So at the moment when the switch has been closed, the capacitor will behave like a short circuit. Okay. In this case, the current passing through the capacitor, we can actually apply, in order to find the current passing through the capacitor, we need to apply current divider law. So let's write it. So it is akin to a short circuit. So I0 plus, the moment after the switch being closed, we have 7.5, which is the initial current here, or the value of the current source, using current divider law, 20 divided by 30, and this is going to give me 3 milliamperes. So the initial current is 3 milliampere. Again, I need to, in order to find the expression, I need to find the final current, and I need to find the final, I need to find the time constant. So what's the final current here? What's the final current passing through the capacitor? Yes, sir.
0.
Why?
Because the capacitor will behave like an open circuit. And
Exactly.
only voltage.
Exactly. So as t approaches infinity, the capacitor the current is 0. Now, Ibrahim?
Doctor, for the current divided law, I think it should be 20/50, isn't it?
Oh, okay. Yes. Okay. Now, I found the initial value. I found the final value. I need to find the time constant. So the time constant is tau equals to RC. This is RC circuit. So R equivalent equals to R Thevenin. What is the Thevenin resistance seen by the capacitor? Ziad?
The 20,
Why?
because it's a short open circuit.
Not really. So if we draw it like this, first of all, we need to deactivate the source. So we'll have capacitor 30 kilo. We have 20 kilo. This is open. This is open. And what's the time constant seen by this capacitor? Rahim?
0.1 microfarad times 50 kilo.
Yes, the Thevenin resistance is 50 kilo ohm. So it's going to be 20 plus 20K plus 50K, and this is going to be plus 30K. And this is going to be 50K. So the time constant will be 0.1 micro multiplied by 50K, and this is going to give me 5 milliseconds. So now I have every quantity that I need to write the expression. So I of t will be I final plus I initial minus I final. And this has to be true for t greater than 0 plus, because this is the current across the capacitor. So I final is 0, I initial is 3, so the expression is 3 e to the power 1 over 5 milliseconds is 200. And the unit here is milliampere. Okay. Okay, now we're done with the first part. So the second part is asking us to find the voltage across, or before that, there's another way actually of solving this problem. What you can do is actually, you can you can find the current, we can find the voltage passing through the capacitor, and then take the derivative. This is also applicable. But we started with the initially with the value that we have to, or the expression that we are interested in. So the second part is asking us to find V of t. So what is V of t? V of t is the voltage across the 20 kilo ohm resistor. So what's the value of, what's the expression for V of t? So what do you think? What do you guys think? What do you guys think we should do here? Okay, Ibrahim.
We first should find the initial value of V of t, which will, by Ohm's law, it will be 7.5 times 20 kilo.
Okay, Ibrahim, what you said is absolutely correct. But the big picture, what do we need? Mohammed?
So, Doctor, isn't the the current equal to C dV? Sorry, the voltage equal C dl di over dt.
Yeah.
So can we just integrate to find the current?
No, you cannot do that. This is a capacitor, not an inductor.
Oh.
Okay. So, what Ibrahim said is actually correct, but in the big picture, the thing that I'm looking for is actually we need to apply KVL here. So we have V of t, we have the voltage across the capacitor and the voltage across the 30 kilo ohm, and this can be done using V of t. This is a voltage that we're interested in. We need the voltage across the capacitor. The voltage across the 30 kilo ohm resistor is actually the current multiplied by the voltage. We find the current in the first part. So I of t, which is I of t multiplied by 30k. So all what we need to do is to find Vc of t. So Ibrahim, what is Vc of t?
It is 7.5 milliampere times 20 kilo ohm.
Exactly. So the initial value is 0. The final value is actually 7.5 multiplied by 20 kilo ohm. Why? Because if you look here, the capacitor will behave like an open circuit. So the current will not flow in the capacitor branch. So the capacitor will be in parallel with the 20 kilo ohm resistor. And the voltage of the 20 kilo ohm resistor is 7.5 milli multiplied by 20k. And this is going to give me 150. So Vc of t is, in this case, is 150 minus 150. The time constant should be the same as the time constant that we found previously. The unit is volt, and this one is true for t greater than or equals to 0. So now I can go ahead and substitute. I know the value of the current. I know the expression for the current from the previous part. I just found the expression of the voltage across the capacitor. So V of t will be something. Okay, there's something weird here. Okay, so I need to figure out a way. But anyhow, so now all what I need to do is substitute. So if I substitute, I will get 150. I substitute the value of the current of the voltage across the capacitor plus the current multiplied by the resistor, and this will give me the final value of the voltage. Okay, we still have one more exercise on this subject, then we will move to the following section, and this will be inshallah covered tomorrow. Allah yatikum al-afiyah. We'll see you inshallah today if you want to show up. Any questions? مهند؟
معلش يا دكتور اليوم السيشن اللي هو الساعة 5 بيكون في نفس التيمز هذا صح؟
اي نعم.
شكرا.
حسن؟
السيشن بيكون ريكوردد ولا؟
It depends. If only one person show up, it will not be recorded. I did once one session and only one.